Hello, good day everyone and fellow researchers. I am Mrs. Katrisna. It is a pleasure to be here today to present our research title, Optimization of Eudragit RS100 PVP-K30 and Lactose in the Theophylline System Release Matrix tablet using simplex lattice design. Our model drug is Theophylline, a BGS class 1 substance, while it boasts highly solubility and permeability, leading to rapid absorption. This unfortunately results in significant plasma fluctuation. Combined with this narrow therapeutic index of 10 to 20 micrograms per milliliter, there is a constant risk of toxicity if blood levels are not strictly controlled. To address this, our research proposed a system release matrix tablet system. We have engineered a synergistic combination of three key components, which is the first is Eudragit RS100, which is act as our primary hydrophobic polymer. It creates a physical barrier to control drug diffusion. And then the second is PVP-K30, a hydrophilic polymer that facilitates the formation of diffusion pores upon contact with gastric fluid. And then the third is lactose, which is for modulate the porosity of the matrix and supports the performing of the PVP-K30. And by optimizing the ratio of these excipients, we aim to achieve a highly controlled and predictable drug release profile, which is essential for maintaining therapeutic efficacy while ensuring patient safety. Moving to the materials and methods, our study utilized Theophylline PP as the active ingredient with a combine of Eudragit, RS100, PVP-K30, and lactose as the matrix system. To find the optimal formula, we implemented a simplex lattice design with 14 experimental runs. We varied the concentration of our three main excipients while keeping the dose of theophylline fixed at 200 mg per tablet. And then the tablet were prepared using the wet granulation method, followed by drying at 60 degrees Celsius and compression into 508 and 0.7 milligram tablet. Finally, we evaluated both the granule and the finished tablet with a primary focus on the dissolution profile at pH 7.2 to ensure the effectiveness of our system release system. Now, let's discuss the result for granule physical characteristic. As shown in the summary table, we evaluated several parameters, including flow rate, angle of repose, bulk density, tap density, compressibility index, and Hausner ratio. Each parameter was modeled into mathematical equations to understand how our components interact. And the key findings section at the bottom provides a clear visualization of this interaction. The blue column indicate an increase in parameter, and then the straight one column indicate the decrease in the parameter, and the blue polka column indicate that the polymer is not significant to the model. Most importantly, all the tested formula fell within the acceptable pharmaceutical range, such as the compressibility index remaining below 18% and the Hausner ratio near 1.2. It indicates that our granules have excellent flow properties and we will suit for the compression stage. And then we evaluated the finished tablets based on average weight, hardness, and friability. The results show that all formulation produce tablet with constant weight. It's 495.888 to 521.545 milligrams. In turn, of mechanical strength, the hardness achieved a robust running of up to 12.299 kilograms, while friability remains very low in most runs, which is essential for withstanding handling and packaging. The key finding section at the bottom provides a clear visualization of this interaction. The blue column is indicate an increase in parameter, then the strip column indicate a decrease in the parameter, and the blue polka is indicate that polymer is not significant to the model. Overall, this physical parameter confirm that our matrix system is capable for forming stable and high quality tablet. Now, let's examine the dissolution response at time 360 minutes, which is the most critical part of our study. As shown in the counter plot, the color gradient provides a clear visualization of how excipient influence drug release. The transition toward red areas indicate a significant increase in dissolution, while the transition toward blue or green indicate a decrease or a more retarded release profile. Based on our mathematical equation and the plot, Eudragit RS100 has a negative coefficient. That's meaning it effectively acts as a diffusive barrier to retard drug release. You can see this in the green colored region at the top of the triangle. Conversely, PVP K30 has the strongest positive impact as a potent paragon. It significantly accelerates release as shown by the deep orange and red areas. And then the lactose also contributes to increasing release by enhancing matrix porosity with a p-value of 0.0205. This model is statistically significant, allowing us to precisely control by Theophylline release by adjusting the ratio of the three components. And then we finally arrive at the optimal formula and validation stage. Based on the simple lattice design optimization, we identified an optimal composition consisting of approximately Eudragit is 10.462%, and then PVPK30 is 28.679%, and the lactose is 5.859%. This specific combination yield a desirability value of 0.913, which is very close to 1, indicating that the formula is highly ideal and meeting all our target requirements. To validate this model, we compare the predicted values from the software against our actual experimental result using a one sample t-test. As you can see in the validation table, nearly all responses, including flow rate, hardness, friability, and dissolution, that showed p-value greater than 0.05. This means there is no significant difference between what was predicted and what achieved in the lab. Although the pop density, this is show a slight statistical difference. It remains well within acceptable pharmaceutical limits. This successful validation confirms that our mathematical model is highly reliable for predicting the characteristics of the substance release system. The next, let's evaluate the release target and kinetic model of our optimized formula. On the left, the bar chart compares our optimized formula result against the USB 20 and 25 targets. As you can see, the release profile shown in the dark tail. This stays consistently within the minimum and maximum target range from the first hour through the sixth hour. This confirms that our formula successfully achieved the desired sustained release criteria. To understand the mechanism of this release, we performed kinetic model feeding, as shown in the right-hand graph. Among the various models tested, the Higuchi model provides that the best fit with exceptional high R square. Oh, excuse. The R square value of 0.9769. This indicates that the drug release is directly proportional to the square root of time following a metric-controlled diffusion of fiction diffusion mechanism. Physically, this means Eudragit RS100 effectively serves as protective barrier, while PVP-K30 and lactose successfully create the necessary diffusion channel or pores to maintain a steady drug release over time. And then Theophylline release mechanism from the optimized formula. The release mechanism of theophylline from the optimized formula consists of 4 distinct stages. The first is the dissolution medium penetrates the matrix tablet, causing it to disintegrate into individual matrix granules. And the second, the hydrophilic component, PVP, K30, and lactose, this is absorb the medium and dissolve, thereby creating a pores within the insoluble Eudragit RS100 matrix. And the third is these pores develop into an interconnected network of microchannels which expands the contact surface area between the medium and drug. And the fourth, this is theophylline diffuses out through the pore network. This process follows the Higuchi model, where the amount of drug release R square is directly proportional to the square root of time. And Eudragit RS100 act as the barrier scaffold, while PVP-K30 and lactose function as channel-forming agent to create the diffusion pathway. Consequently, the release of theophylline is highly controlled and reproducible, as evidenced by Higuchi with R square is 0.9769. To conclude our study, there are 3 key takeaways. The first, we have proven that variation in Eudragit RS100, PVP-K30, and lactose concentration significantly influence the majority of granule and tablets parameters, including flow properties and drug dissolution at time 360. And the second, we successfully identified an optimal formula with composition of approximately Eudragit RS100 is 10.462%, and then PVP-K30 is 28.679%, and then the lactose is 5.859%, with high desirability of 0.913, and then our experimental validation confirmed that there is no significant deviation from predicted values, proving the accuracy of our optimization model. And then finally, the drug release mechanism was confirmed to follow the Higuchi model, ensuring a controlled, reproducible, and consistent motor diffusion profile that meets our therapeutic goals. As I close this presentation, I'd like to share a quote that keep me motivated throughout this research. In the end, everything will be okay. If it's not okay, is it not yet the end? Thank you. I'm Mrs. K30. Goodbye.